Welcome to the Explainer. Have you ever wondered what invisible hand is guiding literally every single movement in our universe? Why things move, and maybe more importantly, why they don't just stop on their own? Well, today we're going to make that invisible rule visible. Let's start with a situation pretty much all of us have experienced. Picture this. You place a little stuffed animal right on the dashboard of your car. You're sitting at a red light, it turns green, and you hit the gas pedal, maybe just a little too hard. Suddenly, that stuffed animal comes flying right off the dashboard and lands squarely in your lap. Why exactly does that happen? Because, it feels like the toy was thrown at you, right? But the physics of what's actually occurring in that split second is completely different, and it perfectly introduces the hidden rule governing everything that moves. So here is our roadmap for today's Explainer. We'll start with the invisible rule of motion, then look at the history of a misconception, dive into Newton's first law, clear up inertia versus momentum, and finally look at saving lives with inertia. Let's jump right in. Number 1. The invisible rule of motion. Okay, here's the absolute mind-bending reality of our dashboard scenario. That stuffed animal isn't moving backward at all. When you hit the gas, your car rapidly accelerates forward. The stuffed animal, however, is simply doing what all matter inherently wants to do. It wants to stay exactly where it is. It resists the change in motion. So while it really looks and feels to you like the toy was launched backward into the cabin, what actually happened is that the dashboard was pulled out from under the toy. Your car moved forward, the toy stayed put in the air for a fraction of a second, and then gravity just pulled it straight down into your lap. Moving on to part 2, the history of a misconception. For a really, really long time, humanity fundamentally misunderstood how motion works. Back in the 300s BC, the ancient Greek philosopher Aristotle claimed that the natural state of all objects was simply to be at rest. He thought every object had a proper place, and if you pushed a block across a table and it stopped, well, it stopped because it naturally wanted to rest. And honestly, this sounded so perfectly logical to everyday observation that we just accepted it for nearly 2,000 years. It wasn't until the 1500s that Galileo finally tested this idea with actual experiments and discovered a hidden force called friction. And then shortly after, in the 1600s, Isaac Newton came along and formalized this entirely new understanding. Galileo used a beautifully simple thought experiment to break that 2,000-year-old illusion. He imagined a ball rolling down a slope. Naturally, its speed increases. If it rolls up a facing slope, its speed decreases until it reaches the exact same height it started from. But then Galileo asked an absolute genius question. What if there is no second upward slope? What if the surface is perfectly flat and we magically remove all the friction? He realized that without the invisible opposing force of friction rubbing against the ball, it wouldn't ever stop. It would just roll on that flat plane forever. Things don't naturally want to stop. They are forced to stop. Which brings us right to section 3, Newton's first law. Building on Galileo's work, Newton gave us the law of inertia. Inertia is defined as the tendency of an object to resist changes in its state of motion. Let's break that down because it's super important. It means an object at rest, like our stuffed animal, wants to stay at rest. But equally important, an object in motion wants to keep moving in a straight line at exactly the same speed. It resists change. And the amount of resistance depends entirely on mass. The more mass an object has, the more inertia it possesses. Basically, matter is just wonderfully, predictably stubborn. Now, if you take one thing away from today's Explainer, please let it be this, because it's literally the #1 mistake people make when they learn this stuff. Inertia is not a force. There is no invisible hand pushing Galileo's ball forward, and there's no mysterious energy holding the stuffed animal in place on your dashboard. Inertia is just a fundamental property of matter. It's what remains when you take all the actual forces away. If you want to see this stubbornness in action, you can actually build what's called an inertia hat right at home. You just take a metal wire coat hanger, snip off the hook, bend it into a symmetrical M shape, and tie 2 equal weights, something like tennis balls, to the ends. Carefully balance the center point of that M right on the top of your head. Now, if you slowly spin your body around in a circle, an amazing thing happens. The hat doesn't spin with you. The weights stay exactly where they were, hanging in the air, while your head just turns underneath them. Because you aren't applying a direct rotational force to the weights, their inertia keeps them perfectly at rest. It's a brilliant little trick that proves matter fiercely resists changing what it's doing.
All right, moving to section 4, inertia versus momentum.
We hear these two words thrown around interchangeably in everyday conversation all the time, but in physics, they're totally distinct. Inertia, as we've said, is a property of matter. It's simply the object's resistance to any change in its motion. Momentum, on the other hand, describes how much motion an object actually has. Momentum is the product of an object's mass and its velocity. So think of a massive truck rolling down a hill. Its momentum is the actual force and speed of its movement. Its inertia is the stubbornness that's going to make it incredibly difficult for the brakes to stop that movement. Momentum is the motion, inertia is what keeps that motion going. Here's a classic trick that illustrates inertia perfectly, completely independent of momentum. Imagine a playing card resting horizontally on your finger with a coin sitting on top of it. Right now, that coin is completely at rest. It has absolutely zero momentum, but it does have inertia. If you quickly flick the edge of the playing card, the card shoots out. And because the friction between the slick card and the coin is so low, you aren't applying enough force to the coin to change its state. Its inertia stubbornly keeps it exactly where it was in the air, and it drops straight down onto your finger. No momentum at all, but plenty of inertia. And that leads us to our final stop, Section 5, Saving Lives with Inertia. This isn't just about fun parlor tricks, it's literal life-or-death engineering. If you're in a car traveling at 60 miles per hour, everything inside that car, including you, is also traveling at 60 miles per hour. If the car hits a wall and stops suddenly, the car's momentum drops to zero. But remember Newton's first law? An object in motion stays in motion? Your body has inertia. It doesn't know the car stopped. It wants to keep moving forward at 60 miles per hour until an external force acts upon it. And if you aren't properly restrained, well, that external force ends up being the windshield. This is exactly why seatbelts were engineered. And the coolest part, they actually use your car's inertia to save you from your own inertia. Inside the seatbelt mechanism, there's this small, heavy pendulum hanging perfectly straight. When the car brakes suddenly, the pendulum's inertia causes it to just keep swinging forward. That forward swing pushes a metal stop directly into the teeth of the seatbelt gear, locking the strap instantly. It's a completely mechanical, instantaneous response, driven purely by the fact that the pendulum wants to keep moving when the car stops. The vehicle's sudden change in motion triggers the lock, catching you long before you hit the dash. We see similar engineering to protect against different types of crashes too. Think about a box flying off a skateboard when it hits a wall. Now imagine you are stopped at a red light and someone rear-ends you. In that scenario, your car is violently accelerated forward. Just like the dashboard pulling out from under our stuffed animal earlier, your car seat is shoved violently forward into your torso. But your head, resting up top, wants to remain at rest. Without a headrest, your body shoots forward while your head stays behind, violently snapping your neck backward and causing severe whiplash. The headrest is explicitly designed to apply a forward force to your head at the exact same time the seat pushes your body, keeping your spine perfectly aligned. All of this, the rolling planets, the sliding coffee cups, the incredible safety mechanisms in our cars, traces perfectly back to this foundational text from Isaac Newton's Principia published hundreds of years ago. Every object perseveres in its state of rest or of uniform motion except insofar as it is compelled to change. It's actually quite poetic in its simplicity, isn't it? A 300-year-old realization that still governs every single movement in our modern universe. So I leave you with this thought to ponder. Once you really understand inertia, you start seeing it absolutely everywhere. It's the reason a spaceship doesn't need an engine constantly firing to glide through the vacuum of space, and it's the exact same reason your coffee sloshes over the rim of your cup when you take a really sharp corner. Where will you spot the invisible hand of inertia today? Keep your eyes open, watch how the world resists change, and I'll catch you on the next explainer.